Hey there. This video we're looking at Coulomb's law. Coulomb's law describes the electrostatic force of attraction or repulsion between or among charged objects. I have here in my picture a plus charge, which is right here, which you could say could be a single proton because it has one positive elementary charge, and over here we got in red the negative electron, -1 elementary charge. The proton is much more massive than the electron, so this is not to scale. It's simply here to represent that we have a positive charge and a negative charge. Coulomb's law states something about the attraction or repulsion that these charges feel and how strong that force is. So I could go back to using our trusty vector arrows for describing the force here, its direction and its magnitude. That's what's represented by my arrow. So let's say that I have a positive and a negatively charged object. Each of these things, a positive charge and a negative charge, what kind of force do they feel? They feel an electrostatic force that attracts them because they are opposite charges. So the positive charge will feel some force of attraction this way to the right, and then I'll also have a force vector for my electron or -1 charge feeling a force of attraction towards the positive charge. Now this is an example of another Newton's third law action-reaction force pair. This is the same amount of force, so these should be the same length green arrows, but they are pointing in opposite directions. They're both the same type of force, an electrical force or electrostatic force. And if we want to know exactly how strong that force is, that's what Coulomb's law tells us. So I'm going to write F sub E for electric or electrostatic force, and we'll make that a capital E. And we got to think about what are some of the things that matter in terms of determining the strength of this force. The direction we know because we know opposite charges will attract, same charge type will repel. So that gives us the direction. These are opposite charges, so the arrows are pointing towards the other one. In terms of how strong it is, if I have a larger amount of charge, then I'll have a stronger amount of force. And if they're closer together, their force is going to be stronger. So we use Q to represent charge. I'm going to call this one lowercase q1, and this red negative charge is lowercase q number 2, just to keep track of them. So I've got the product of those charges helps determine how strong that force is. So there's Q1 multiplied by Q2. Okay, that's going to be in my numerator because the stronger the amount of charge or the larger the amount of charge, the stronger the electrostatic force. And downstairs, I want to be able to represent the distance between them. So if we go with our dotted orange line here, that's going to be the distance between these two objects. We'll symbolize that with the letter R for radial distance. Then downstairs, I have R because if they get closer together, then R is smaller, and that'll make the force stronger. And if they're very far away, then R is a larger number. When this denominator gets to be a larger value, then that means the total value of our fraction goes down, the force goes down. So they're closer together, stronger force. And this relationship of force, electric force, to the distance between the objects is not it's not inverse, it's not linear, it's inverse squared, just like the gravitational force. So this is R squared. If we get the charges twice as far away, then you have 1/4 the electrostatic force or electrical force. If they get 3 times as far away, then you get 1/9 of the electrostatic force because that is a inverse square relationship. Just like our universal gravitation equation, we do have a constant, which we will symbolize with the letter K, that goes in front of our fraction, and this is just a constant that is determined experimentally. And it's the ratio between the electrostatic force and the product of the charges up top divided by their radial distance squared that's separating each other. That ratio is a constant K, which is called Coulomb's constant. Coulomb's constant, K, which is approximately equal to 9 times 10 to the 9 Newton times meters squared over coulombs squared. Remember, the unit for charge, the unit for these charges is the coulomb, right? So that's the unit for charge. My charges are symbolized by green. The unit for charge is the coulomb, and that's symbolized with a capital C. Okay, and then my units for my force down here are going to be newtons of force. newtons of force. My distance, we got our base unit, this is a distance between the charges in meters. Okay, so we've got coulombs of charge up top, symbolized by our Qs, Q1 and Q2. That's in coulombs. The unit, we have a keyboard appearing. We have downstairs the radial distance in meters, and this Coulomb's constant is in Newton meters squared over Coulomb squared. A giant number, 9 times 10 to the 9. That's a huge, huge number. The universal gravitational constant, that was about 7 times 10 to the minus 11. Okay, so here's the equation that relates our electrostatic or electrical force between charged or among charged objects to the amount of charge up top in the numerator. More charge, greater force, and it relates it to their distance between each other. If we're further away, we have a much, much smaller electrical force. This is R squared. And then this K is just our constant. It's a physical constant, doesn't change. All right, what if we had a picture of two negative charges? If we drew that real quick, I have a negative charge and another negative charge. They're separated by this distance R. First, I want to think about the direction of the electrostatic force. They're like charges. They're the same type of charge, so they're going to be repelled. So they will experience a force. We'll say this is the force. Here's Q1, Q2. So this is the force of Q1 acting on Q2 to repel that right side negative charge. Over here, I have an equal in magnitude but opposite in direction force. That's going to be the force of Q2 acting on Q1. So it's the same amount of force, but opposite directions, just like before when they were opposite charges. It was still the opposite direction force, but still the same magnitude. Hello again, keyboard. Goodbye. But down here we have two negative charges, so they're going to repel. Same thing would happen if we had two positive charges, they would repel. We want to know how strong is this force, this electric force between the two of them, and I know that's going to be K, Coulomb's constant, that's 9 times 10 to the 9, times the magnitude, the amount of charge 1, multiplied by the amount of charge 2. We symbolize those with our Qs. Those charge amounts are in coulombs, that's the unit, divided by R squared, R being the distance between those two charges. And this total value here will be a force in newtons. A force in newtons, to repeat what we said just above. Okay, if I wanted to go and calculate that exactly, like if it were just two electrons at, say, 1 meter apart, then I would need to know what is the charge of the electron in coulombs. So that's something we can actually find. This keyboard really wants to be used. It keeps popping up. Electron charge magnitude, I got right up here, is approximately 1.6 times 10 to the minus 19 coulombs. So we'll say that's the elementary charge, is 1.6 times 10 to the minus 19 coulombs. Did I just record that right? Really small, right? So I said earlier in another video, 1 coulomb is a lot of charge. So an electron just has 1.6 times 10 to the minus 19 coulombs is its amount of charge. That's different from saying that the elementary charge is 1. Right? So an electron, we said, has a charge of minus 1, but this is how many coulombs that one elementary charge is. It's a different unit. All right, so that's the amount of charge. Coulomb's constant, we already know that's our K, is 9 times 10 to the 9. 9 times, that's not a times, 9 times 10 to the 9 Newton meters squared, or Coulomb squared, our units. All right, so let's say we just have two electrons that are 1 meter apart. So if it's 1 meter apart, then R is 1 meter. That'll simplify everything. So let's see, what is the magnitude of the electrostatic force between two electrons that are 1 meter apart? I have K is 9 times 10 to the 9. We'll do some nice, easy scientific notation. That's my K value. Boop. Then I've got charge 1 times charge 2. So that means I have 1.6 times 10 to the minus 19. That's the charge for charge 1. And then multiplied by the same charge. So I could write this over again, or I could just square it. Divided by, let's move this over a little bit. We're going to divide that by our distance, which I'm saying, let's just pretend it's 1 meter apart. So this R value is going to be 1 meter squared. All right, so that simplifies things. You want to see exactly how much that is? Let's do up top first, where we have our 1.6 times 1.6. 1.6 squared, I think 16 squared is 256, right? So this should be 1.6 times 1.6 should be 2.56. And then we've got our exponents minus 19, minus 19. When we're multiplying, we are going to add those and not multiply them. So we'll have 38 as our exponent. So I'm going to leave my Coulomb's constant 9 times 10 to the 9 multiplied by what's upstairs is 2.56 times 10 to the minus 38. And then we've got just 1 downstairs, so that's going to go away. Let's do a little rounding. I have about 2.5 times 9, so 9 times 2 is 18, plus another 4 or so, about 22. So we'll have about 22 times 10, and then I got to add my exponents 9 and 38, so I'll have times 10 to the minus 27, and that's going to be a force in newtons. Not too much. 22 times 10 to the minus 27 newtons of force. Now this is a certain amount of force just from the electrostatic force between two electrons that are 1 meter away. This Coulomb's law equation looks very similar to our universal gravitation, which I'll remind you of right here. The force of gravity is equal to big G, universal gravitational constant, times the product of the masses divided by the square of the distances between them. So you could do the same thing here to see what the gravitational force is between two electrons and kind of compare the strength of these forces. Which one's stronger, electrostatic force or gravitational? Because electrons still have mass. Big G is our 6.67 times 10 to the minus 11, so I'm going to round it to 7. And then the mass of an electron is super tiny. We can find it. It's right over here. 9.11 times 10 to the minus 31 kilograms. We're going to call it 9 times 10 to the minus 31 kilograms. All right, we'll say they're 1 meter apart again. 1 meter apart. So this Fg equals, this force of gravity between two electrons is going to be our universal gravitational constant times our mass is 9 times 10 to the minus 31. We have 2 of those, 2 electrons, they're 2 masses, so we'll square it. Divided by distance 1 meter apart squared is just divided by 1. So Fg, I got to deal with my numerator there first. So I have 9 squared, which is 81. Let's call it 80. And then I have 80 times 10 to the minus 62. 7 times 8 is 56, so this is 560 times 10 to the minus 73. And we've got, let's change this so we have agreeing order of magnitude. So I got 56. If I divide my prefix by 10, I got to multiply my exponent by 10. So if I multiply this by 10, then I'll have times 10 to the minus 72. And that's in newtons. The gravitational force between two electrons is about 56 times 10 to the minus 72 newtons, and the electrostatic force between the two electrons is going to be 22 times 10 to the minus 27. So this is a much stronger force. The electrostatic force is much stronger than the gravitational force. All you got to do is look at these exponents. Minus 27, yeah, that's a really small number. Minus 72 is a much, much smaller number. So this force of electrostatic interaction between the electrons is way stronger than gravity. So if we go up and we look at our picture again, it's like, well, all right, I got two objects with mass here, our electrons. They're going to be attracting to each other because they are objects with mass. But they also repel because they have both the same sign. They're both negatively charged, so they're going to have an electrostatic force of repulsion. And the reason why we see those electric charges repel and fly away from each other instead of being pulled into each other by gravity is because the gravitational force is so much smaller, so much weaker compared to the electrostatic force. So there's a good comparison. This is another example of an inverse square law. Inverse square law, meaning that the electric force varies inversely with the square of the distance between the two objects. Just like the force of gravity from universal gravitation varied inversely to the square of the distance between the two objects. There's Coulomb's law, and that's about it for now.